Well, this is a really interesting problem. We're going to have a graph of a vector-valued function represent the intersection of the upper half of this ellipsoid. Remember what an ellipsoid looks like. Its cross-sections parallel to the x, y, and z axis are all ellipses or else don't exist. And so this would look something like some kind of a weird football. So the upper half of it would just be, like if I solved this for z, that would be the equation of the upper half of it. Unfortunately, my graphing software won't do a very good job of graphing that one, so I had to draw it by hand. But in the parabolic cylinder, I have that one drawn, or a piece of that one drawn here. Y equals x squared with the z-axis like this. Here's y equals x squared in the xy plane, but then it keeps going up. However, it would keep going up like a good old vector valued function would, or like a good old surface would, rather, I should say. But it intersects this upper part of this ellipsoid, right? Remember, it's just that upper part of that. So the graph is just this red part, and that's what we're talking about, and what I'm trying to describe, that red part with a vector valued function. Difficult problem. So we could start by saying let x equal t, and since y equals x squared on this surface, the whole blue and green surface, then we could say y equals t squared, and solving this ellipsoidal equation for z, we get this. I could have done that earlier, right? If you solve this for z, multiply both sides by 4, subtract all this junk from both sides, trust me, you would probably come up with this without too much difficulty. We're going to replace x in this with t, and y in this with t squared, and we get the z, here it is. So now our vector valued function is, we're going to say that x equal t, y equals x squared. Remember why we're doing that, because it's on the three-dimensional version of this parabola. The parabola extended out along the z-axis might be a better way to say that. And so the vector valued function, here's our x times I, here's our y, remember it was this, times j, and here's our z, which we actually had to solve for by plugging in our value of x equals t and y equals t squared, and there is our vector valued function. And so let's see, I guess we better figure what the possible values of t are to describe, remember, just this intersection. We have to have a beginning and an end for where this curve is, and the beginning and the end would come from the fact that what's underneath this radical has to be greater than or equal to 0. And I solved this, if you'll bear with me, I just used my software to solve this, so it was probably a bad idea for me to make up a problem this ugly, because now you're going to get scared and think you'll have to be able to come up with solutions of equations like this by hand. And I would say, no, please don't worry about that, you don't. But I made that problem up, and I just thought it was pretty cool. But wow, look at those t limits. You don't see limits like that very often, or maybe I should say you don't see intervals that look like that very often.